Now it is your turn to practice. Let's work through 3 short labs. You will build a tree, count its leaves, and measure its height. This is Lab 1. Your goal is to build a small tree by hand, then print all 3 recursive traversals. It is the same 5-node tree from the earlier check. This is the tree. 20 is the root. Its left child is 35 and its right child is 3. 35 has 2 children of its own, 9 on the left and 41 on the right. Your task is to write build, pre-order, in order, and post-order, then print all 3 sequences. Pre-order should give 20, 35, 9, 41, 3. In order should give 9, 35, 41, 23. Post-order should give 9, 41, 35, 3, 20. Pause the video and try it yourself first. Did you build the tree? Let's look at one clean solution together. First, we make the 5 nodes. Make node 20, 35, 3, 9, and 41. Each one starts with no children. Now we link the root. We set 20's left to 35 and 20's right to 3. Then we link 35. Its left is 9 and its right is 41. The other 2 nodes are leaves, so they need no links. Finally, we return N20, the root. Now the whole tree is reachable from that one pointer. The 3 traversals are exactly the ones from this chapter, so we do not repeat them here. For the cost, building each node is big, O of 1, so 5 nodes is big. O of n each traversal visits every node once, so it is also big, O of n. This is Lab 2, a trace lab. Your goal is to count the leaves in this 6-node tree. First count them by hand, then check with count leaves. This is the tree. 15 is the root, with children 60 and 2. 60 has children 44 and 91. Node 2 has a single child, 7, on the left. A leaf is a node with no children at all. Go through the tree and find each leaf. Pause and count them yourself before we run the code. How many leaves did you find? Let's write the function and check. The first line is the base case. If x is equal to null, there is no node here, so we return 0. Next we test for a leaf. If x arrow left is null and x arrow right is null, this node has no children, so it is a leaf. We return 1. Otherwise the node has at least one child. We return the leaves in the left subtree plus the leaves in the right subtree. The recursion adds them up for us. The cost is big O of n. We visit each node once, the same shape as tree size and tree height. Here is the driver that runs it. The comment tells you the tree build makes 15 points to 60 and 2, 60 points to 44 and 91, and 2 points to 7 on the left and nothing on the right. In main, we build the tree and keep the root pointer. Then we call count leaves on the root and print the result. For this tree it prints 3. The 3 leaves are 44, 91, and 7. And we free the tree before returning. Remember from the post-order slide why that works. Free each child before its parent. This is Lab 3, the challenge. Your goal is to compute the height of a tree in 2 different ways, and then confirm that both answers agree. The first way is recursive. It is exactly the tree height function from this chapter, the one that takes the taller of the 2 subtrees and adds 1. The second way is iterative. You run level order in rounds. Snapshot the current queue length, then process exactly that many nodes, in queuing their children for the next round as you go. Each full round is 1 more level of height. Try both versions and make sure they give the same number. Pause here and give it a go before the solution. Let us look at the iterative height together. You already know the recursive version, so we work through the level order form instead. First, the base case. If root is null, the tree is empty, so we return -1, matching the convention from earlier. We put the root into the queue. The queue now holds the first level, just the root. Height starts at -1, so an empty tree and a single node tree both come out ripe. The outer loop runs while count is greater than 0, that is, while the queue still has nodes. This is the key trick of the whole lab. We snapshot count into level size. That is the number of nodes in this level, taken before we add any new ones. Then the inner loop runs exactly level size times. It processes only the nodes that belong to the current level, even though the queue is growing underneath it. Inside the inner loop, we dequeue. Move front forward with a mod and take one off count. If that node has a left child, we enqueue it. Those children belong to the next level down, not this one. And if it has a right child, we enqueue that one too. After the inner loop finishes one full level, we add one to height. One round equals one level. That is the whole idea. Both versions are big O of n in time. The recursive one uses big O of h space on the call stack. The iterative one uses big O of w space in the queue, where w is the widest level. That is a real trade-off, not just a matter of style. On a chain, the recursion is the expensive one, and on a wide, bushy tree, the queue is. And that wraps up binary trees. You can now build them, walk them 4 ways, measure them, and avoid the common bugs. Great work, and I will see you in the next chapter.